Yeah, fine. So any dynamical system shows a variety of different behaviors in terms of the asymptotic states, which are the attractors of the system. And yesterday we have used the reservoir computing concept, where it is a basically deep learning framework where we only update the output weight in the readout in order to training the machine, and so that later on we can use the same machine for the prediction purpose. And the idea here was, what we have done one example yesterday is that there is the chaotic time series. We have taken the example of Lorentz system, and we train the system for one state variable and try to predict the other state variables in time. So in the entire process, our parameter was fixed. Okay, and but in general, when you look at any dynamical system, there are two different possibilities may exist, that sometime there can be a change in the disturbance in the parameter. It can be a change in the internal parameter or the external forces, which may influence the dynamics of the system, and the system move from parameter P1 to P2, and this may lead to a transition from one state to the another state. There is another possibility that for a given set of parameter, system may show the multi-stability. So the system shows the multi-stability in terms of the initial condition. Some initial condition lead to the one attractor and some may go to the another attractor. There can be a two or more than two coexisting attractors. So what we will discuss today is that can we also predict the multi-stability in such dynamical system using the reservoir computing, or can we also learn the dynamics at the different parameter, or can see the unseen attractor which are not trained during the training period. So the overview of my talk will be, I will just introduce the parameter aware reservoir, which is the slightly modified version of the reservoir which we have studied yesterday, and then I will use that for the multi-stable system dynamics learning as well as the multi-parameter dynamic learning. So as I said that in the common reservoir computing, during the training phase, we update the output weight and then we do the prediction. And now what we will do is, since we are interested to have a prediction of the unseen attractor at the different parameter where the system goes from one phase to another phase, or the attractor at the same parameter which was not trained in the multi-stability system. So what we do is, we will have a parameter aware reservoir. That means that we also give the information about the parameter to the system. So while inputting the input information of the state variable of the dynamical system, we also feed the parameter to the reservoir, and we do the same process what we have done for the common reservoir computing. So let's look at the one example where we can go from the local to the global dynamic prediction. I have given the population model example where system can show a steady state solution for a given parameter P1, and it may also show an oscillatory population states in the another parameter P2. So as we change the parameter, you can see that system shows the transition at a particular critical parameter value from a steady state to the oscillatory state, called the half bifurcation. So now the question is, by training at a given parameter in a particular state, maybe the steady state or oscillatory state, can we predict the another state at a different parameter? So we use this the parameter aware reservoir computing, and before I go for these two examples, I would like to give you the quick overview of the reservoir dynamics analysis, how the internal dynamics of reservoir is updated with the input of the external dynamical system. So as I mentioned that we also feedback the parameter epsilon of the dynamical system. So this is the state of the dynamical system given by equation 1. You have the updated state R of the reservoir is given in terms of the previous state with the weight matrix here, and the input weight with the input of the state variable U, which is the given dynamical system, and then there is a epsilon which is also fed to the reservoir. And now then we do the training, and during the training part we update the output weight. Okay, so once the training is done, so this we got the W out optimized weight. We can replace the input variable U by W out times R, and then this can be simplified to this difference equation, which is equation 3 for the state of the reservoir. So reservoir is now getting the information of the input variable U of the given dynamical system, and that can be further simplified to this the equation 3, which can be we can do the numerical computation for the steady state solution of this difference equation, which is the, say, R star, which is the fixed point of this equation 3, and we can do the Jacobian matrix calculation for the at the given R star, and the eigenvalue analysis of this Jacobian will tell that what kind of dynamics is there for the reservoir. Now, if there is any change, it carries this information for in terms of epsilon also. If there is any change in the epsilon, that will shift your eigenvalues of the reservoir, and your reservoir dynamics can also have a kind of bifurcation there. So let's first talk about the multistable system. As I mentioned that the multistable systems are having a more than one stable state at a given parameter, and that depends upon the initial conditions, and set of initial conditions going to the one or another attractor is called the basin of attraction. Okay. And we also have the multistability in the climate dynamics. I have given one example here where you can have a warm and snowball conditions overlapping as a function of solar constant, where the temperature shows the two different states simultaneously at a given solar constant. Now, to take example which is not from the climate dynamics, and it is the example of the another multi-stable system which is given by this 4 couple differential equations, and it shows the hidden attractors and also multi-stability in terms of the fixed point and oscillatory state. So I have plotted here the parameter space epsilon and beta, which are the 2 parameters of the system, and the region 1 is the state of the unbound state of the system, and region 3 and 4, they are the fixed point and the oscillatory state regions, and region 2 gives you the coexistence of steady state and oscillatory solutions together. So now the idea is that if we train the machine at a given parameter for a given attractor, say for example the oscillatory or fixed point attractor, can we also predict the another attractor which was not trained? So we use this the parameter aware reservoir, where we input the epsilon also along with the state variable of the system, where in addition to these 4 the input x, y, z and u, we also give the epsilon as an input to the system. And what we do is we do the training in the period 2 region for 3 different epsilon values, and we try to predict the entire bifurcation diagram, and you can see that the predicted bifurcation is in a very close approximation with the original one. So there are some, you can see that there are some changes in the attractor, but qualitatively they show the similar kind of the state at the, and all the bifurcation points can also be matched with the original dynamics of the system. And we have also done the entropy of the predicted system with the original system. So what else we have done is that we have trained, because we have trained this for this 3 parameter values epsilon, which is 0.36, 0.38 and 4, which was the training, and we could predict the attractors which are far away from the training point, like for example epsilon 0, 0.28 and 0.65. So by training in the periodic region at a given epsilon, we could identify the chaotic fixed point and other periodic orbits which are far away from the training data set. Yes.
Data is all periodic.
Yes. Yes.
What is the accuracy?
Yes.
But quantify distance or how much of an error are you making
Yeah, there you can see that there is a attractors are quite different, not exactly. Yeah. In the we have done the this one is the we have not done the analysis for the difference of attractor in terms of the geometrical properties and all, but in another case we have done the analysis by taking the large number of samples and do the different order parameters to see that whether you get the same attractor or not, the transition.
as you go for smaller epsilon, it gets worse and worse. But it's actually quite good at epsilon 0.1 or 0.2.
Yes.
It's really good, and it gets bad at 0.
Yes.
But so, is there some measure that you can, some, hesitate to say order parameter, but some kind of some quantification? I mean, that would be useful.
Yes. Yeah, that can be done, but we have not done that here. Yeah, so this was the serious problem at the epsilon close to 0, that it was not exactly the same attractor, but showing the chaotic behavior. So we could see that here we can see the unseen attractors far away from the training data set. And we also try to predict the basin starting for 3. So what we have done is we have trained the dynamics for 3 different this epsilon values, and we have predicted the basin at a different parameter value 0.4 with the hyperparameters given by this. And you can see that this is the original basin and this is the predicted one. Still there are some changes in the boundaries, especially in this the second region, but we could fairly well predict the all the different states and their basin here. So with this, we next move to the multi-parameter prediction, where system can have the some changes in the internal parameter, or it can be external forcing. So while you are doing the training at one particular parameter value, and on the run, the system may change the parameter, or there can be external perturbation to the system, and now you are far away or you are moved from the training data set. So can we also predict the dynamics there, and especially when you have a more than one parameter which are changing, like including internal and external. So we went for the one parameter and two parameter bifurcation diagram and prediction with a very minimal data set. So the motivation for this was that suppose you have some internal and external loads for a like P1 and P2, and you design the object at given say 2 data sets, and then you know the structural response to these 2 parameters, and then you want to see that how the system will behave if there is a sudden change in the parameter. Okay, so you have to have an information of the entire parameter space, that what will be the response of a given P1 and P2 in the entire grid. So if you are doing this with the traditional approach, it will be more expensive in terms of energy and time. So can we use the reservoir there to predict the entire grid response of the system? So with this, we have used the Duffing oscillator, the forced Duffing oscillator. If you remember that yesterday, what we have done is we have used a single node reservoir where we can use the single Duffing oscillator for the prediction purpose. In this today's problem, we are using the eco-state network, which is a random network, as a reservoir, and the input is the state of the Duffing oscillator, which we want to predict. So this is the equation of the Duffing oscillator, and we set the parameters like this, and you can see that by the change of the amplitude or the frequency of the external the forcing, the oscillator can show the variety of different behaviors starting from oscillatory period 1, period 2 to the higher periods as well as the chaotic states. So we want to design a digital twin which can predict the dynamics at the different parameter values. So we again use the parameter aware reservoir, and we also input this FT, which is the external forcing to the system. Now, so as I said that our objective is that if I just train the system for two set of parameters, I want to set with a minimal set of parameters, it can be 1 or 2. So if I set it for 0.49 and 51 here, can I predict the other states of the system? So I use the auto regression reservoir design. This is my oscillator, this is the reservoir dynamics, and I optimize the W out, and then it can be with this regression. And then once it is there, then I can use I can replace this equation 2 by 5 and use this for the next round of the prediction period. So in the prediction, I have the information which is the U, which is the predicted value of the state, where I also have the state of the oscillator as well as the parameter, the external forcing F cos omega t. So what I do is I train for these two parameters, and then I try to predict the different states. Here you can see that again they are qualitative agreement, but they are still not same. But broadly you can say that system shows the same kind of the behavior. At least you can do the classification whether system is in the one type of attractor state or another type of attractor state. So we have with this training, with the minimal data set training with the two parameters only, we could generate the bifurcation diagram, and we have compared the original bifurcation with the predicted one, where the training was done only for the two set of parameters. So now here we have done some rigorous analysis, and we have had some order parameters also to quantify the predicted the values with the original one. And you can see that here we have done this for the two parameter space, F and omega, where this F is amplitude and frequency of the external forcing. This is the original state dynamics, and this is compared with the prediction. You can see that there is a fairly close match with the original dynamics in the prediction phase, and there are some deviations there, and we could also identify all the transition points, period 1 to period 2, period 2 to period 4, and all these things. Except period 2 to period 4, there was some a drop in the accuracy. Otherwise we could identify the exact transition point also with a fairly well accuracy there. So, and what we have done here is, if you look at the training, we have done this 4 sample of training at these two parameters, F12 and omega 12, the pair of these two, and we got the only 4 initial training data set, and we could predict all the different states here. And this was done for the multiple runs also. And here I will show you that this, if you look at the Yeah, it is. Yeah. So it will not move because of the PDF. So if you look at these four bifurcation diagrams, and they have generated for 1, 2, 3, and 4 samples, you can see that for 2 or more samples, the prediction was good. So you need at least 2 samples to get the all the bifurcation points which are in agreement with the original points of the bifurcations. And with this, I would like to conclude here that that we have investigated the data-driven approach to infer the dynamics of a multi-stable system using the eco-state network, and we could get the whole bifurcation diagram with the significant accuracy. And we have also done the prediction of the dynamics of externally driven duffing oscillator for the unseen parameters at it can be like starting from the one parameter value where the system is in the one state, and we can predict the another type of attractor at the different parameter values. And this we have done for the both one parameter and two parameter bifurcation diagram, which were obtained with the good accuracy there. So I would like to acknowledge all my collaborators for this work and my lab there at Central Institute of Rajasthan. Thank you.
Questions? I'll go from this direction. Ambika.
Okay, so when you predict, so the dynamics from a system where you have in the learning process only say the stationary solutions or the periodic ones as you showed, and so then what is the mechanism? So the dynamical mechanism, because this is nothing else than a dynamical system, what we see. So why you can predict also the chaotic solution. So why does it work? So what is the reason? So to say, can you do a kind of bifurcation analysis for the whole dynamical system? So including your reservoir, so to explain why you can do that.
So my understanding is that when we do the training for one parameter, so there are two dynamical system. One is the input dynamical system, another is reservoir, and during the and since they are coupled to each other, so they are kind of in sync with each other, and the reservoir learn the dynamics of the input dynamical system for a given set of parameter. But now when you do the training for one parameter, how can you learn the unseen attractor at the different parameter? For that, my understanding, I'm not sure. What I understand is because any dynamical system which we are trying to predict for a different attractor at a different parameter values, so that is a inbuilt attractor of or one of the state, the asymptotic state of the dynamical system, which was unstable at the training parameter. So you have so when you change the parameter from P1 to P2 or P3, so system is going through the bifurcation from attractor A1 to A2 and A3. But the system which is at the parameter P1 showing the stable dynamics of attractor A1 is also having a unstable periodic orbits present there, and the system is also learning that, and when you change the parameter, it can show that the unstable orbits or the unstable chaotic orbits which are now stable at the different parameter. So
to the chaotic attractor, because then all your periodic solutions which you had in the very beginning would be unstable at this point.
yes,
but the
other piece is not possible. Yes, this is my kind of from chaotic to periodic. This is my intuitions, and I have this. Yeah, other way is not understandable.
There is not this unstable.
Yes.
How dynamic specific. For example, if you train the system with the dumping, can it predict the transitions in those?
No. I guess no. Yes. Yes.
That context, the real that it cannot predict. Some data from the rest of the system.
Yes.
Your training system. Yes.
As
Explain the question. I can't.
For example, any new data also it may not be able.
new data, but it may be from the same data. So as long as it is major data, but then again it is the from the where the training is done, and you are doing the prediction from the same. But it yes, yes, correct.
Anybody at the back? So, thank you so much, Manish. Those were two very clear talks. I
Thank you.
can imagine you do very good teaching that, and I think, but I would like you to say just, I mean, this is a general question. Where do you think we could use this machinery in, let's say, climate protection?
It's a difficult question. So before coming here, I was going through so I found one recent paper on archive, where people have used the reservoir in the climate modeling. But I have not seen. So it is mostly it is the given dynamical system, and then you are predicting not from the real data. Yes.
So as you learn other things from the reservoir, as you give a training pattern, you could give a climate training pattern. But application from the application's point of view, like for example, what Udit was saying, and so on, the machine learning concept is very important. Yes, thank you.
Thank you.